Hi everyone, this is lecture 20, Respiratory System. So today we're going to talk about the basics of the respiratory system all in one lecture. This is going to be a long one, so grab a coffee, grab some notes, and you may want to take a break partway through. So we're first going to talk about the basics, and then we're going to talk about the process of ventilation. That is the process of just moving air in and out of the lungs. And then we're really going to get into the details of oxygen and carbon dioxide exchange, transport, and the general control of respiration. So the respiratory system, just to remind you of the anatomy, is made up of the nasal passages, which begin up here in the nasal cavity, the pharynx behind the throat, the larynx, which contains the voice box, the trachea, which stretches down the neck, the lungs, which contain the air sacs, and the bronchi, which branch from the trachea as the airways into the lungs. The trachea and the bronchi contain cartilage to keep them open as the air is moving in and out of the respiratory passageways. The alveoli are the air sacs, microscopic air sacs in the lungs that contain simple squamous epithelium for the purpose of diffusion, very, very thin-walled air sacs, so that the oxygen and carbon dioxide can diffuse easily in and out of the blood supply. So the respiratory system works very closely with the circulatory system because the job of the respiratory system is to bring in air to replenish oxygen in the blood and then to bring out the carbon dioxide from the blood and remove it in the air that is breathed out. So to do that, we have to move air in and out through the process of ventilation. We have to exchange gases with the blood, mainly oxygen and carbon dioxide. And as we are able to regulate, particularly the carbon dioxide levels of the body, the respiratory system plays an important role in pH regulation of the blood. Because as carbon dioxide waste builds up, the blood will get more acidic. And we'll talk about that and give you guys the chemical equations that will show you how carbon dioxide makes the blood more acidic. Moving air in and out also allows us to use the chemicals in the air to smell what is around us, and the movement of the air allows us to produce sound through the vocal cords in the larynx. So just some anatomy pictures to review. Okay, so I want to make sure that we clearly define ventilation versus respiration. So most people think that respiration is breathing, and that's not the case. Ventilation is breathing. So ventilation is just the movement of air in and out of the lungs, and that is conduction of air. Respiration is actually the gas exchange. So respiration is the diffusion of oxygen and carbon dioxide. This requires the coordination of both respiratory and circulatory systems. So external respiration is bringing oxygen and carbon dioxide from the external environment to and from the tissues. That is, oxygen will be brought in from the air into the air sacs of the lungs, and then from the lungs diffuse into the blood, and then from the blood diffuse into the body tissues. Carbon dioxide will be then produced in the body tissues as they're performing metabolism, and that will diffuse into the blood and be sent from the blood to the lungs, and will diffuse into the air sacs of the lungs, into the air, and then we will breathe the air out. Cellular respiration, then, is the term for the metabolism of the nutrients in the cells using oxygen and releasing carbon dioxide waste. So we're going to use a similar diagram to this throughout today's lecture. So here is just a basic overview, and as this lecture gets complicated, because it will, I want you guys to always, when you start feeling a little bit lost in what we're doing, I want you to back up and remember this diagram. What is it that we are trying to do? Where should the oxygen go? Where should the carbon dioxide go? So always remember that as the air comes in, the oxygen should go into the blood. From that, the oxygenated blood will travel, being pumped by the heart, to the tissues. And we then want the oxygen to go into the tissues so the tissues can use it for cellular respiration. Now, where should the carbon dioxide go? The carbon dioxide is produced in the cells as a byproduct of breaking down our fuels, carbon-containing fuels like carbohydrates and fats and proteins. That carbon dioxide waste should then go back into the blood, travel through with the deoxygenated blood through the heart and up to the lungs, and then it should be removed from the blood into the lungs where we can breathe it out. So everybody knows we breathe in oxygen and we breathe out carbon dioxide. It's not actually true. We breathe in a mixture of gases, but we diffuse in oxygen and we diffuse out carbon dioxide. So let's first talk about the process of ventilation, and this is really where the air is conducted down through the respiratory passages. So air is going to be conducted from the atmosphere to the lungs, and it must be conditioned. So the airways from the nasal passages all the way to the tiniest of bronchi, the bronchioles, are going to make that air more hospitable to the body. So it's going to moisten the air. It's going to warm the air, filter and condition the air as it moves down into the lungs. So as the air is moving down and there's no diffusion happening, we call this region of the respiratory system the conducting zone. So the conducting zone stretches from the nasal passages all the way to the terminal bronchioles. From there, once we are in the alveoli, or once we start seeing alveoli appear in the bronchioles, then we can do gas exchange. Hopefully this is review for you guys from anatomy. I know I stress this a lot in my anatomy class. Hopefully your anatomy instructor did as well. There's no respiration that can happen until you're at the level of alveoli. And as the alveoli that are doing the actual gas exchange, starting on the respiratory bronchioles. So ventilation is the movement air in and out of the lungs through breathing. Inspiration is breathing air in. Expiration is breathing air out. And this requires coordination of breathing muscles as well as pressure gradients established through the action of those muscles. So let's first talk about inspiration. So take a second to put your hand on your chest and take a deep breath in. So, which way did your chest move? It should have expanded. So when we breathe in, we use the diaphragm, which is the lower muscle below the ribs, and we use the external intercostal muscles surrounding the outer portion of the ribs and stretching around the back of the ribs to expand the chest. When we expand the chest and open up the thoracic cavity, what that does is it creates a pressure gradient. I'm going to show that to you in a second, but for now, just remember, inspiration is expanding the chest. We use the diaphragm and the external intercostal muscles to do that. That is a normal resting inspiration. If we then take a huge deep breath, right, we can add the muscles. You might have seen the muscles of my neck start to poke out through that really deep inspiration. Those are in addition to the diaphragm and external intercostals. The forced inspiratory muscles are the sternocleidomastoid and the scalenes. So these are neck muscles that can, in addition, pull up even more on the chest cavity to expand it even further for a very deep inspiration. So let's look at what this does. So when the diaphragm is relaxed, it is in this shape here. When the external intercostal muscles are relaxed, then the chest cavity is as the diaphragm contracts, it makes a sort of dome shape and increases the volume of the thoracic cavity. When the external intercostal muscles contract, they lift up the rib cage. Now for expiration. Expiration is the movement of air out of the lungs. So again, take a deep breath in and now release it. What happened? Your chest went up and out for inspiration and down and in for expiration. So this actually doesn't, in the resting phase, take any muscle coordination. So when you go from a passive inspiration to a passive expiration, all you have to do is relax the diaphragm and relax the external intercostals. That's resting. But if you want to take a huge expiration, so do that, you might feel when you try to push air out, you might feel the engagement of a couple of extra muscles. The engagement there will be the internal intercostal muscles and the abdominal muscles. So your oblique muscles and your abdominal muscles can then push and compress the chest and abdominal cavities. When we do that, we decrease the volume of the chest cavity, and that pushes air out. So this is what happens during expiration. During expiration, we passively relax the diaphragm and passively relax the external intercostal muscles. But if we want to add an additional forced expiration, we can then compress the abdomen and push harder on the internal intercostals. So we can engage the internal intercostals and the abdominal muscles to compress the chest cavity and compress the abdomen. So how does this actually work? We're expanding the chest cavity and compressing the chest cavity, and what that does is creates a pressure gradient. So ventilation is the movement of air in and out of the lungs, and this happens due to volume and pressure changes in the lungs. So air will move along a pressure gradient from high to low. So here's how it works. Inspiration, we breathe air in. You expand the chest, that increases the volume of the chest. When you expand the chest cavity, all of the same molecules were in there. Those same molecules now have more space. When we give more space to the molecules, there is less pressure on the chest cavity. So opening up in volume decreases pressure. What that does then is creates a gradient where the pressure outside of the lungs is lower than the pressure inside of the lungs. So let's draw this out. Okay, so in the chest cavity, what you have is a certain amount of air molecules, right? When we expand the chest cavity by contracting the diaphragm, so we contract the diaphragm and the external intercostals, that expands the diaphragm out this way and out this way. Expands the chest cavity out this way and out this way. But you have the same molecules. Now, if you look at the pressure of those molecules against the wall of the chest cavity, you now have lower pressure inside the thoracic cage. When you lower the pressure inside the thoracic cage, you now have a pressure gradient where the air outside wants to move in from high to low. So you open up the chest cavity, and that causes air to move in. That is inspiration. Then we go back the other way, and we compress the thoracic cage, when we compress the thoracic cage by relaxing the diaphragm and relaxing the external intercostals, then that decreases the volume of the chest cavity, and that causes higher pressure inside, which will then create a gradient for the air to move from high to low outside. So that is expiration. So inspiration is increase in volume, decrease in pressure. Expiration is decreasing in volume, increasing in pressure. And those gradients cause the air to either move from high to low in the lungs during inspiration or from high to low out of the lungs during expiration. So this can be completely explained by the changes in volume of the chest cavity. And in fact, we have simple models that we can use with increasing and decreasing volume to show how that will suck air in when you increase volume and push air out when you decrease volume. So a lot of people think, so do this again, right? Breathe in. For us, it seems simultaneous, right? When you breathe in, it feels like you're sucking the air in and then the chest cavity expands, but think about it again. Your chest cavity actually expands first, and then the air moves in. So try to change your sort of natural inclination to think that you suck the air in first. That actually comes second. Volume changes first, then the air moves. Volume changes back down, then the air gets pushed out, and that is ventilation. So this is based on a law called Boyle's law, which says that the pressure exerted by a gas in a closed container is inversely proportional to the volume. So this is a very fancy way of saying when volume goes up, pressure goes down. So they have an inverse relationship. When one goes up, the other goes down. So just like we did in the chest cavity, when you expand the chest cavity, volume goes up, and that causes pressure to go down. Then air wants to move in. And then the reverse is true. When you decrease the volume of the chest cavity, when you compress the chest cavity, that decreases the volume of the chest cavity. That increases pressure. You're pushing more on those molecules. Now the air wants to move out. So the movement of the respiratory muscles changes the volume of the thoracic cavity, and then the air follows. So here's a visual of that. If you didn't understand my drawing, this one might be better, right? So let's say we start sort of at this neutral volume, certain number of gas molecules, volume 1, pressure 1. Now let's expand the chest cavity, open it up, and increase the volume, but keep the molecules the same. Now if we read the pressure inside that container went way down, such that if you have the same air pressure outside, now the air pressure relative to the pressure inside wants to move in. When we do the opposite, when we go from sort of this neutral state and then we press on the air, that decreases the volume, increases the pressure, and now the air wants to move out to equilibrate. Okay, so here's a summary of the muscles. So remember, external intercostals are actually for inspiration. So the X's are for inspiration. The internal intercostals are for expiration. So it's vice versa. The diaphragm contracts for inspiration and relaxes for expiration. And then we have the accessory muscles. So in addition to this pressure-volume relationship, we also want to track the pressure gradients that are very important for maintaining normal breathing. So I've already alluded a little bit to the pressure in the atmosphere being important. So to actually measure these and not just look at the volume-pressure relationships, we need to put some numbers to this. So we're going to look at the pressure in the outside air, the atmospheric pressure. We're going to look at the pressure in the lungs, the intraalveolar pressure. And we're going to look at the pressure from the air sacs in the lungs across the chest cavity, which we call the intrapleural pressure. So first, atmospheric pressure. The pressure outside of the lungs is 760 millimeters of mercury. That's at sea level. This will change if you go to higher altitude, but generally we're just going to do these calculations at sea level. So the pressure in the atmosphere is 760 millimeters of mercury, and that will be fairly constant. The pressure inside of the lungs is then going to equilibrate with the pressure in the atmosphere. So it's going to be plus or minus 760. It's going to vary then as the lungs expand, as the diaphragm and external intercostal muscles contract, and then as the lungs recoil and goes back down. So this will determine whether the air will enter or leave the lungs because the lungs are open to the environment. So the lungs can equilibrate with the environment because the airways are continuous from the nasal passages down into the lungs. So the pressure in the atmosphere is 760, and the lungs are going to try to reach 760 every time you change their volume. So if the pressure inside of the lungs drops below 760, then air will move in. It's going to go from high to low. If the pressure in the lungs goes above 760, then the air will move out. It'll go from high to low. So let's draw this out again, just in case you guys are getting a little bit confused. Okay, so we're looking at now the pressure outside in the atmosphere, which is 760. So we're just going to call that pressure atmosphere. And that then is going to be able to equilibrate with the lungs. I'm just going to draw one side of the lung just for simplicity's sake. So the pressure outside is 760, and let's say the pressure inside of the lungs was neutral, 760. What's going to happen? Nothing, right? So they're normal, 760, 760, no airflow. Now let's say from this sort of neutral position, we now contract the diaphragm and the external intercostals, and we expand the chest cavity. So we then increase the volume of the chest cavity, increase the volume of the chest cavity, and the pressure then drops to, say, 759. Doesn't take a big change. We increase the volume, the pressure goes down because of that Boyle's law. We now have 760 in the atmosphere and 759 in the lungs. Which way is the air going to go when you expand the chest cavity? In. Good, so that's inspiration. Air will move in. And now let's relax and even compress the chest cavity so that we now decrease the volume and increase the pressure. So if we decrease the volume back down by relaxing the diaphragm and relaxing the external intercostals, we maybe even compress with the internal intercostals and the abdominal muscles. Now we still have 760 outside, but now the pressure went up to, say, 761. If the pressure goes up because we've compressed the thoracic cavity, which way is the air going to go? Yep, it should move out from high to low, and that will be expiration. Okay, you guys get it? Good. Now we're going to move to not just the atmosphere and what's inside the lungs, but there's one more important factor. This is the intrapleural pressure. So intrapleural refers to the pleural space surrounding the lungs. So remember from your anatomy that the lungs are surrounded by a pleural membrane. This is a serous membrane that secretes fluid, so there is fluid surrounding the lungs, which keeps the lungs tight against the chest cavity, but also reduces friction between the lungs and the chest cavity. So what happens here is that the pleural sac is completely closed to the atmosphere. So all of this blue space is its own sac. It is not open to the air, and it maintains a pressure that is around 756 millimeters of mercury. So at rest, this pleural space, which contains fluid, is going to be 4 millimeters of mercury less than the pressure of the atmosphere. So we're going to call this P pleural or intrapleural pressure, and it's going to be around 756. This is set by the way that the lungs develop in the chest cavity and by the suction of this fluid against the chest and lung wall. So what happens is that the lungs are now suctioned to the chest cavity by this negative pressure in the pleural space. Why is it a negative pressure? It's negative because it is much lower than the outside environment and lower than the lungs. So this negative pressure makes sure that the lungs are coupled to the chest cavity. What that means is that as the chest cavity moves, the lungs will move along with it. So it does no good, right, to contract the ribs and contract the diaphragm if the lungs stay behind. So we can contract the ribs, contract the diaphragm, expand the lungs, contract the ribs, contract the diaphragm, expand the chest cavity, and then the lungs, because of this intrapleural pressure, the lungs are going to go with the chest cavity and expand along with it. And that's very important because it's not the chest cavity that we want the air in, it's the lungs. So this pleural pressure is between the lungs and the chest cavity, and it's -4 or 756 millimeters of mercury. It is not going to equilibrate with the atmosphere because it is closed and filled with fluid. It's very important for keeping the lungs attached to the chest cavity. As the muscles move the chest cavity, then the lungs will follow. So this is sort of the way that the pleural sac develops, if this picture helps you. So imagine that the lungs are a lollipop, and they then, as they develop, they push into this surrounding double-layered serous membrane, which is like this water-filled balloon. So as the lungs develop, they push into and get surrounded by this membrane, but the membrane the entire time stays closed. Then eventually, as the lungs reach their final development, they are open to the atmosphere, but the pleural sac, or this double-layered serous membrane with fluid inside, is never open to the environment. So we have pleural sac around the right lung, which is independent, and a pleural sac around the left lung, which is independent. And this negative pressure inside the pleural sac, or the intrapleural pressure, makes sure that the lungs are stuck to the thoracic cavity, so that as the thoracic cavity expands, the lungs will move along with it. So let's do a summary of these pressures and finish our drawing here. So we'll start here with neutral again, and now I'm going to draw the pleural sac around this. Let's say it's a right lung. So we had 760 in the atmosphere. We had 760 equilibrated in this sort of neutral phase. And then around the lungs now, we have the intrapleural pressure, which is going to be 756. So your book sometimes refers to this as a -4 pressure, and where that comes from is if you set the outside to 0, then the interpleural pressure will be 4 less than the outside, and that negative pressure creates a suction, making sure that the lungs are stuck to the chest cavity. If we then expand the lungs, I keep doing that, I know. If we then expand the chest cavity to open up the chest cavity and increase the volume, that is then going to open the chest cavity, lowering the pressure inside the lungs, and we maintain an intrapleural pressure that is lower than the pressure outside. But as you pull on the chest cavity, the intrapleural pressure can also, the chest cavity expands, that can actually pull on or open up the pleural space a little bit as the lungs are moving along with it. So it can actually go down to, say, 754. And that then would be sort of like a -6, and that will pull even further on the lungs to really ensure that the lungs are coupled to the chest cavity. Then expiration is passive. Everything moves down at the same time. So expiration will go back down to 756. So this, no matter what happens with the chest cavity, the pleural pressure is always lower than the atmosphere. So here's a summary of that. So the pressure in the lungs decreases as the inspiratory muscles contract and increase the volume of the chest cavity. Here are some example pressures. Atmospheric pressure 760, alveolar pressure 759. The air will move in until the alveoli and the atmosphere are equal at 760. For expiration, the pressure in the lungs will increase as the lungs recoil. Some example values there would be 760 in the atmosphere. The alveolar pressure could go up to 761, and the air will move out until we reach equilibrium again. The pleural pressure, these are hard to say that 10 times, right? The pleural pressure is going to fluctuate with the pressure of the chest cavity and the pressure in the alveoli. So as the chest cavity expands from normal, sorry, this doesn't match my regular drawing. So as the pressure in the chest cavity expands from before inspiration to inspiration, then that pleural pressure can drop, creating even more of a suction on the lungs to the chest cavity. Okay, take a moment to pause and make sure you understand these pressure gradients that cause air to move into the lungs and air to move out of the lungs. Now we need to define this a bit more formally. So this difference between the alveoli and the pleural cavity and the atmosphere is approximately -4. So this negative pressure makes sure that the lungs stick the pleural sac to the thoracic cavity. So the pressure in the pleural cavity is always less than the pressure in the lungs, causing a negative pressure sticking the lungs to the chest cavity. This is called the transmural, so across the walls, the transmural pressure gradient. This is absolutely vital to the function of the lungs and to allow ventilation to happen. If we lose pressure in the pleural cavity, that can cause the lungs to no longer stick to the chest cavity, and that can lead to collapse of the lungs. And then no matter what you do, if the lung is collapsed and not stuck to the chest cavity, no matter how you expand the chest cavity, the lung is not following. Until you relieve that pressure and then the lungs stick back to the wall, then you can breathe again. So here's a diagram of the transmural pressure gradient. So it's important that it is different between the pleural space and the atmosphere and between the lungs and the pleural space. Both of those differences need to exist and be less than in the pleural cavity. Here's what happens when you have a puncture either in the chest wall or a puncture in the lung wall. If you have a puncture in the chest wall, then the air will move into the pleural cavity and equilibrate. That then will cause the lung collapse because everybody will be at 760 and that lung will no longer be coupled to the chest cavity. The same thing would happen if you have a hole in the lung between the lung and the pleural space. That will equilibrate again with the pleural space and create 760 all around, so no more negative pressure in the pleural space. The same thing will happen. You'll have a collapsed lung. So until this is relieved, until the pressure in the pleural space can be reduced or the hole is patched back up, the lung will be collapsed and you will not be able to breathe from this side of the lungs. So let's look then at a graph which shows these pressure differences. So here's the pressure. We're going to start at 760 in the atmosphere, and now we're going to follow what happens during inspiration. So during inspiration, the volume of the chest cavity increases, which decreases the pressure in the alveoli. Then during expiration, the volume of the chest cavity returns and even compresses further, and that causes the pressure in the alveoli to go up and air to move out. The transmural pressure gradient should then stay always at least 4 below the atmosphere and the alveoli to make sure that the lungs are following the chest cavity. So the factors for ventilation are the pressure gradients, which we have just gone through. There is also how much resistance you have in the airways or opposition to airflow and how much the lungs are elastic, which is compliance. So we just spent some time on pressure gradients. Okay, so the pressure gradients ensure ventilation. And now we're going to talk about resistance and compliance. So in addition to pressure gradients, airway resistance can also affect ventilation. That is, if the airways are creating a lot of opposition to flow. So we talked about resistance in blood vessels, and it's the same idea. It's the same kind of fluid dynamics and the same equation. The flow depends on the change in pressure, so this high to low pressure gradient, and it can be reduced by an increase in resistance or a blockage of airflow. So there are 2 ways to change resistance in the airways, and this is through the smaller airways or the bronchioles. So if we constrict the bronchioles, that decreases the radius, and when you decrease the radius, that increases resistance because it's a smaller space. So we're now closing the airways. Thank goodness this is way more intuitive than what happens in blood pressure, right? So we're closing the airways, that increases the resistance, and that will lower airflow, right? Close the airways, then we have very low airflow. This happens normally at rest as the body is just kind of conserving. So the parasympathetic input at rest will cause bronchoconstriction. There is also pathological bronchoconstriction that can happen during inflammation, during allergies with the release of histamines, with excess mucus production in chronic lung disease. Finally, bronchodilation. So we can take the airways and open them up. If we take a small airway and we open it up, this will lower the resistance and increase airflow. This will happen with sympathetic nervous system input. The sympathetic nervous system actually expands the bronchioles, it relaxes the smooth muscle in the lungs, so it does the opposite to what it does in the blood vessels, and that's through epinephrine. This happens during increased activity because what do we need for increased activity? We need more oxygen to the tissues, so we need to increase the airflow. So sympathetic nervous system input, namely through epinephrine, will open up the bronchioles and increase flow. Lung compliance refers to the ability of the lungs to stretch and distend during ventilation. So remember that the lungs are coupled to the chest cavity, and as the chest cavity moves, the lungs have to stretch and recoil along with it. So it's important that the lungs have elastic tissue so they can stretch and recoil. They also have water on the surface of the alveoli. This creates a surface tension that enhances the recoil and opposes the alveolar expansion so that they can also stay open. The pulmonary surfactant is a fluid that is secreted by the alveolar cells that balances the effects of the water to make sure that the surface tension is not too high. So this allows then the airways to stay open and be more elastic, soften and recoil. So water alone is not enough to keep the airways expanding and recoiling. We need to add this fluid secreted by the alveolar cells to balance out that water. That makes sure that the surface tension doesn't get too high and increases the elasticity and recoil of the airways. So this is a summary diagram of the forces on the alveoli. So there are forces that keep the the air sacs open, the alveoli. The transmural pressure gradient makes sure that the lungs are stuck to the chest cavity. That opens up the air sacs. And pulmonary surfactant, which is also keeping the air sacs open and not too tightly recoiled. The forces promoting alveolar recoil or alveolar collapse in the extreme case will be the elasticity of the connective tissue, so that allows them to stretch and then recoil, and the surface tension from the water. That allows the recoiling during expiration. So in lab, we're going to measure lung volumes and talk about various conditions which can affect lung compliance, elasticity in the lungs, which can affect resistance or airflow in the lungs. So stay tuned for measuring all of these and looking at how they can change with resistance and compliance issues and disease conditions. Okay, this would be a good time to take a 5-minute break. We're now going to get into the gas exchange that happens where the oxygen and carbon dioxide will flow between the air sacs and the blood. So gas exchange is where the respiration actually occurs. So this is between the alveoli and the pulmonary capillaries, or the blood surrounding the alveoli. So first the air has to get in through the process of ventilation, but once the air reaches the air sacs, it now has to diffuse oxygen out to the blood and carbon dioxide back in to the air sacs. So we have a respiratory membrane that is very, very, very thin and has some specialized structures to allow this gas exchange to happen. So if we zoom in on the air sacs here, you'll see this is the inside of the air sac which is blue. So we've got a couple of air sacs here. So there's a single alveoli or an alveolus. It has a very thin wall, simple squamous epithelium walls lining the alveoli. And then it is right next to the capillary. So here's a cross section of a capillary, a pulmonary capillary. There's a red blood cell right nearby. So the red blood cell is waiting to pick up oxygen and waiting to deliver carbon dioxide. And it has to get that oxygen and carbon dioxide across the simple squamous epithelium of the alveolus, but also across the simple squamous epithelium of the capillary. So we have two very thin layers between the capillary and the alveolus. The space then between the capillary and the alveolus needs to be very, very small. It's about 0.5 microns. So the capillaries are very close to the alveoli to make sure that diffusion of oxygen and carbon dioxide can happen. A couple of other cells that ensure that the air sacs have the appropriate surface tension and that they stay clean. We have macrophages, alveolar macrophages, which will go around and phagocytose any debris that is in the lungs. We have type 2 alveolar cells that secrete something called pulmonary surfactant. That pulmonary surfactant is what we just talked about, which keeps the surface tension from getting too high and makes sure that the airways can stay open. Type 1 cells are the simple squamous epithelium that make up the walls of the alveoli. So in premature babies, you may have heard that surfactant is not yet produced. So they can stimulate it if they know the baby's going to be premature by giving the baby steroids, but it takes time and it's later in development that these type 2 alveolar cells actually make surfactant. So one of the major conditions in a premature baby is difficulty breathing. So what they'll do in a premature baby to make sure that the lungs stay open is that they will maintain the baby on oxygen to create positive pressure in the lungs and slightly push open the air sacs enough so that they don't collapse. So here's a zoom in of those cell types. So type 1 alveolar cells, simple squamous, making up the walls of the alveoli. Type 2, creating surfactant to keep the air sacs open. And then macrophages to make sure that the air sacs stay clean. The capillaries then are also simple squamous epithelium, and then there's a red blood cell waiting to pick up oxygen and drop off carbon dioxide. Okay, now this is the fun part. You guys ready? So now we need to talk about the diffusion of gases and the actual movement of oxygen and carbon dioxide. So this is going to get complicated, but I'm going to give you the big picture first, and let's draw it out, okay? Okay, so we have oxygen and carbon dioxide in the air. We want to bring that air into the lungs. I'm just going to draw one side of the lungs so that we can put oxygen into the blood and deliver oxygen to the tissues. So I'm going to draw some just tissue cells here where the blood is going to deliver oxygen to the tissues. So oxygen from the air wants to go into the blood, and then the blood will carry that oxygen to the tissues. From there, the tissues are going to do cellular respiration, right? Cellular respiration is going to use oxygen and make carbon dioxide waste. So the oxygen in the tissues will now go down and be used up as the tissues are doing cellular respiration. And then from there, the tissues are going to make carbon dioxide So the carbon dioxide is going to go back into the blood and be carried through the blood to the lungs, where carbon dioxide now will go from the blood into the lungs. So we want oxygen to come in and carbon dioxide to move out. Remember this as we start to go through the nitty-gritty details and it starts to get a bit confusing. So it should go in this pattern. We want to bring oxygen into the lungs, then down into the alveoli. We want the oxygen in the alveoli to diffuse into the pulmonary capillaries. From there, it will get pumped through the heart and through the systemic circuit for the oxygen to get delivered to the tissues. From there, the tissues are going to use the oxygen in the process of cellular respiration and produce carbon dioxide waste. The carbon dioxide waste then should diffuse into the blood and get carried through the circulation, through the heart, and back to the lungs, where the lungs can remove carbon dioxide. How are we actually going to measure this? We're going to measure this by something called partial pressure. So if oxygen and carbon dioxide were molecules in a liquid state, we would just measure straight concentration. But since they're molecules in a gas state, we have to measure something called partial pressure. So in your mind, you can just switch the word partial pressure with the word concentration. It's just a way of measuring the concentration of gas in a total gas mixture. So we're going to use partial pressure and partial pressure gradients to look at the movement of oxygen and carbon dioxide. The principles here are exactly the same as using a chemical or concentration gradient if I were to just give you, osmolarity values like we did in the diffusion portion of this class. So gases will move with their concentration gradients just like other molecules move with concentration gradients. They're going to move from high to low. But in this case, instead of saying concentration, we're going to say partial pressure. So a gas moves from high partial pressure to low partial pressure. And that is in an area where there is more of a gas, it wants to move to an area where there is less of a gas. So we're going to measure the partial pressures of oxygen and the partial pressures of carbon dioxide. I also want you guys to separate in your mind the partial pressure gradients from the ventilation gradients that we just talked about. Totally different. The ventilation gradients are looking at total air in the atmosphere and in the lungs. It doesn't say anything about the individual components of the air. So think of these not as your ventilation gradients, but as your diffusion gradients for concentration or partial pressure of these individual gases. So let's look at our partial pressures. So oxygen in the atmosphere is about 21% of the total atmosphere. If we do the calculations, then that gives us the partial pressure of oxygen in the atmosphere to be 160 millimeters of mercury. From there, the air is going to get mixed in the lungs, so it's not going to be exactly the same as the atmosphere. The alveoli partial pressure of oxygen is closer to 100 millimeters of mercury. It's not a perfect one-to-one because old air gets mixed with new air in the lungs. So this is probably the last time we'll talk about the atmospheric partial pressures. From now on, we're just going to focus on the alveoli and inside the body. So memorize this number. The partial pressure of oxygen in the alveoli is 100 millimeters of mercury. That's very high. That's a good concentration of oxygen. Then the pulmonary capillaries are going to come in with deoxygenated blood. That deoxygenated blood is the blood that was coming from the tissues, right? So that deoxygenated blood is going to have a low partial pressure of 40 millimeters of mercury. Now we have a pressure gradient. the pressure gradient from the alveoli to the blood is 100 to 40 because this is deoxygenated blood that just came from the tissues and it wants to be replenished in the lungs. So that deoxygenated blood has 40 millimeters of mercury, and it then contacts the alveoli at 100 millimeters of mercury. Which way is the oxygen going to go? Well, before you even look at the calculations, think about the big picture. Which way should the oxygen go? The oxygen should go from the alveoli to the blood, because that's the goal, right? The blood wants to pick up the oxygen. The alveoli should deliver oxygen to the blood. So we're going to go from 100 to 40, and that's high to low. So the alveoli are going to diffuse oxygen into the pulmonary capillaries. The pulmonary capillaries are then going to equilibrate such that the blood leaving the lungs is now this same value of 100 millimeters of mercury. So the PO2 equilibrates to return oxygenated blood now to the heart and out to the body. So now all of this blood matches the oxygen level in the alveoli. So that is 100 millimeters of mercury as we're going through, and then down to the tissues. Now from the tissues, we're going to want to deliver oxygen from the blood to the tissues. So how does this work? If we measure the PO2 at the tissues, we find that the tissues, because they're constantly using oxygen, they don't have oxygen stored up. The storage of oxygen is done in the blood. So the tissues are going to be low oxygen, and their PO2 is going to be 40 millimeters of mercury. So now, which way is the oxygen going to move? Well, back up and think about which way should it move. We want the oxygen to go from the blood to the tissues, right? So do the numbers match? Yes. The numbers in the blood are 100 millimeters of mercury, and in the tissues, 40 millimeters of mercury. So that will drop off oxygen into the tissues, and the tissues will immediately use it. So let's look at the actual oxygen exchange in the lungs. So air is ventilated from the atmosphere to the alveoli, and because of that, it mixes old and new air. That means that the atmosphere and alveoli are not exactly the same. The alveoli are a little bit less than the atmosphere, but that's okay because 100 millimeters of mercury in the alveoli is still quite high. So that's a good amount of oxygen, and because now the partial pressure of oxygen in the alveoli is higher than the oxygen in the blood that has just come from the heart, then we're going to diffuse from 100 down to 40. So the alveoli partial pressure of oxygen is 100. The pulmonary capillaries coming into the lungs from the heart are at 40. This is going to trigger gas exchange. Oxygen is going to move from the alveoli into the pulmonary capillaries. Now we'll get down to the tissue level. Because that just equilibrated and the alveoli soaked up the blood with oxygen, that fully oxygenated blood is going to have a PO2 of 100, and the tissue cells are going to have a low PO2 of 40. We now have another gradient for oxygen to move from the blood into the tissues. Okay, yeah, I know, we need to draw it out. Okay, so we are just so the blood that is coming in from the heart that just returned from the tissues is going to have a PO2 of 40. The air is going to have a high PO2 because of all the oxygen in the atmosphere. So that is going to be a PO2 of 100. And now the oxygen is going to move from the air sacs into the blood. That 40 is then going to get equilibrated with the 100, and now the blood leaving the lungs is going to have a PO2 of 100. From there, that highly oxygenated blood is going to go from the tissues and have a PO2 of 100 as it reaches the tissues. The tissues do not store oxygen, so their PO2 is low. Their PO2 is 40. So now we have exchange where the oxygen in the blood is now going to go into the tissues and get used up in the tissues. So it gets used through the process of cellular respiration, and that PO2 then, that oxygen gets used, that PO2 in the tissues goes back down after the equilibriate, it gets used, and now the blood leaving the tissues has a PO2 of 40 because it just got used during cellular respiration. So for oxygen, I want you guys to remember 100 and 40. Those are your two numbers for oxygen exchange. It's 140 at the lungs from the sacs, air sacs to the pulmonary capillaries, and it's 100 to 40 at the body tissues from the systemic capillaries to the body tissues. Okay, now for carbon dioxide. So carbon dioxide is much, much lower in the atmosphere. So I think the number is 0.004%. Don't hold me to that. I can't remember. But the partial pressure of carbon dioxide in the atmosphere is 0.23 when you do that calculation. In the alveoli, the partial pressure of carbon dioxide is actually going to be higher because, again, of this issue of old and new air mixed. So you have high carbon dioxide in the lungs because that is the lung's job to pick up carbon dioxide and remove it in the air. So the PCO2, or the partial pressure of carbon dioxide in the lungs, is 40. Now the pulmonary capillaries coming in. Quick question, don't cheat, don't read it. The pulmonary capillaries coming in, where did they just come from? They came from the heart and they came from the tissues. Are the tissues going to have higher or lower carbon dioxide than the lungs? The tissues are going to have high carbon dioxide. Why? Because the tissues produce carbon dioxide through cellular respiration. So you'll see, though, that this gradient is a little smaller than the oxygen gradient. The PCO2 in these deoxygenated, highly carbonated blood is going to be 46 millimeters of mercury. So the deoxygenated blood coming in from the heart and the body tissues into the pulmonary capillaries is 46. The air sacs are 40. Which way is the carbon dioxide going to move? Well, back up and think about which way do you want it to move. You want it to go from the pulmonary capillaries into the air sacs so that the lungs can remove it and breathe it out, right? So that's what happens. 46 is high, 40 is low. The carbon dioxide is going to go from the pulmonary capillaries into the air sacs, from 46 to 40, and then the lungs will breathe it out and remove it. So now let's look down at the tissue level. What is happening at the tissue level? At the tissue level, the tissues are actually producing carbon dioxide. So as they produce carbon dioxide, then they're going to have a PCO2 of about 46. That production of carbon dioxide then is going to be higher than the PCO2 of the blood coming in. So 46 to 40, carbon dioxide moved from the blood into the air sacs, and that equilibrated and brought the carbon dioxide in the blood back down to 40. This now oxygenated low carbon dioxide blood gets transported to the tissues and has a PCO2 of 40 in the systemic circulation. That PCO2 of 40 is going to then pick up carbon dioxide that was produced in the tissues and move up to a PCO2 of 46. So let's zoom in on this and just look at CO2. I think it's actually easier if we start at the source of the CO2. So if we look down at the tissues, tissues are producing carbon dioxide at a partial pressure of around 46. The systemic capillaries coming in are going to then have a partial pressure of 40, such that the CO2 moves from the tissues into the systemic capillaries. It will then equilibrate 46 to 40, and the systemic capillaries leaving the tissues are going to have a PCO2 of 46. From there, that PCO2 of 46 enters the pulmonary capillaries and diffuses from the pulmonary capillaries into the low carbon dioxide concentration of the air sacs. So 46 now, the concentration in the air sacs is 40. We're going to go from 46 to 40. The carbon dioxide is going to move from the pulmonary capillaries into the air sacs. Yep, I know, we need to draw this one out too, okay?
So back to our diagram. So we're going to start at the source of carbon dioxide. During cellular respiration, the tissues make carbon dioxide waste, and that gives them a PCO2 of 46 millimeters of mercury. That PCO2 is higher than the PCO2 of the oxygenated low waste blood that is coming in. It's low waste because the lungs had removed it. So the oxygenated low waste blood has a PCO2 equal to 40. Now the carbon dioxide is going to move from the 46 to 40 gradient. Carbon dioxide is going to enter the systemic capillaries and give us a PCO2 of 46 in the systemic capillaries. From there, that PCO2 of 46 will get delivered to the lungs, where the lungs have a low PCO2 of 40. And now that CO2 is going to move from the systemic capillaries into the lungs. So the numbers you need to remember for carbon dioxide are 40 and 46. And the direction for carbon dioxide is out of the lungs and out of the tissues, whereas the direction for oxygen was into the blood and into the tissues.
Okay, I know this is a lot of numbers. So again, when you guys start to get lost in these pressure gradients, I want you to remember two things. One, which way should the oxygen and carbon dioxide go? So back up. And then when you have your gradient numbers memorized, the gradients should match and make sense. So if I asked you, we're here in the lungs. Which way is oxygen going to go? Well, the oxygen should go from the lungs into the pulmonary capillaries. Now you should know that the lungs should be higher and the pulmonary capillaries should be lower. And you've memorized these numbers, 100 to 40. Do you see the strategy? Now, what is the value of carbon dioxide in the lungs? Well, we want carbon dioxide to move from the pulmonary capillaries into the lungs. So we're going to go 46 in the capillaries, which is high, to low 40 in the lungs. So use that strategy if you guys are starting to get lost in these numbers. 140 for oxygen, 46 and 40 for carbon dioxide. Here is the summary diagram of how your book puts it all together. You may want to take a moment to piece all these things together and make sure you understand them together with what we have drawn and what the book is telling you. Okay, so the airflow, which is the ventilation, and the blood flow, which is the perfusion, is actually matched in the lungs to make sure that there is enough time for diffusion of the gases. So we call this ventilation-perfusion coupling. So we want to make sure that the blood flow matches the airflow, and there can be problems if they don't. So if the perfusion or the blood flow is too low, let's go down here. If the perfusion or the blood flow is too low, it's too slow relative to the flow of air, then too much gas exchange can occur. That can mess with the gradients in that case. If the perfusion or blood flow is too low, then we want to slow down the airflow. We can do that by constricting the bronchioles and decreasing the airflow to match the slow flow of the blood. If the blood flow is too high, or you have high blood pressure, and that's greater than the airflow, then what we need to do is we need to open up or expand the bronchioles, bronchodilate, to get more air in. That's sort of like the train is leaving, it's going too fast, and the gases or the oxygen and carbon dioxide don't have time to get on and off the train. So if the blood is moving too fast, we need to slow down. If the blood is moving too fast, we need to dilate and increase the flow of the air so that the ventilation or the amount of air coming in matches the perfusion or the amount of blood flowing. That ensures that the gases have the appropriate time to exchange. The levels of oxygen and carbon dioxide will be sensed in the lungs in order to change bronchodilation or vasoconstriction. If the carbon dioxide is too high, then bronchodilation will occur. That will increase airflow. If the oxygen is too low, then vasoconstriction will occur, and that will decrease blood flow to give the oxygen time to exchange, and vice versa. So there is a summary diagram to describe ventilation-perfusion coupling, and this is important to understand that blood flow should match airflow. If we have too much carbon dioxide, then that tends to affect airflow. If we have not enough oxygen, that tends to affect blood flow. So low oxygen can cause vasoconstriction if it's in the pulmonary arterioles. Low oxygen can cause vasodilation if it's in the systemic arterioles. So vasoconstriction in the pulmonary arterioles will slow down the blood flow and allow for more oxygen exchange to happen. That's different than that would happen out in the body, where vasodilation will increase, where low oxygen will increase blood flow to the tissues, because low oxygen in the tissues is saying the tissues are using too much, right? And that's different than not having enough exchange. Okay, that was probably the first hard part of this lecture, which is the partial pressure of gases. Ventilation, no big deal, right? Partial pressure is kind of confusing. Takes some time to understand that. Now we're going to do gas transport. This is the second piece of today's lecture that is really challenging. So again, probably a good place to take maybe a 5-minute break, okay? So we're going to talk about the specific transport of oxygen and carbon dioxide. So between the locations of gas exchange, the oxygen and carbon dioxide can be transported in two ways. The gases can be dissolved in the liquid plasma of the blood, or the gases can be bound to hemoglobin protein in the red blood cells. So first we're going to do oxygen. So oxygen is mainly transported bound to hemoglobin That is the job of hemoglobin, right? We talked about this in the previous blood lecture. Hemoglobin is a specialized protein which is very, very packed in red blood cells. And the job of hemoglobin is to bind oxygen. So 98.5% of oxygen in the body will be bound, oxygen in the blood will be bound to hemoglobin. 1.5% will be bound to oxygen. The reason we need hemoglobin is because oxygen does not dissolve well in liquid water. So oxygen is not very soluble in the plasma, and that is why hemoglobin has evolved to give us more oxygen carrying capacity. Each hemoglobin can bind up to 4 oxygen molecules. So remember for the hemoglobin that you had 4, I'll show it in a second, you had 4 subunits of hemoglobin. Each of those 4 subunits can carry an oxygen molecule. So here's the reaction, hemoglobin plus oxygen makes oxygenated hemoglobin. So hemoglobin needs to bind oxygen in order to carry it from the lungs throughout the body. It also needs to unbind oxygen to deliver it from the circulation to the tissues. So hemoglobin has a very special function. It needs to both load and hold on to the oxygen, but also be able to let go of the oxygen. It doesn't make sense to have money in the bank if you can't spend it on anything, right? So we load up the oxygen and then we can unload it so that it can be used at the tissues. So oxygen should be loaded onto hemoglobin at the lungs and unloaded at the tissues. So if we follow the partial pressure gradients of oxygen and we look at the properties of hemoglobin, it should match this idea. So here is a visual of the 4 subunits of hemoglobin, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So when you have 4 out of 4 subunits of hemoglobin filled with oxygen, then you have 100% binding of oxygen. When you have just 2, then that's 50%. 3, 75%. 1, 25%. So what we're going to do is we're going to look at the binding of hemoglobin and compare it to the partial pressures of oxygen in different environments. And what this really is asking is how cool of a molecule is hemoglobin? And the answer is hemoglobin is super cool. So hemoglobin has these amazing properties to be able to sense the level or the partial pressure of oxygen in its environment. And hemoglobin will bind and hold on to oxygen when oxygen is low. And it will bind and hold on to oxygen when oxygen is high so that it can store oxygen. So when money is plentiful, you keep it in the bank. But hemoglobin is also very generous and will donate oxygen when it gets into an environment where oxygen is low. So the hemoglobin will carry the oxygen throughout the body systems, through the systemic circulation, and when it gets to a neighborhood that has low oxygen, it's generous and it will let go of its oxygen and deliver it to the oxygen poor environment. So hemoglobin's like Robin Hood, right? He takes from the rich and gives to the poor. So if we follow the partial pressures of oxygen, when oxygen levels are high, when it is in an oxygen-rich environment, hemoglobin is going to bind to and load oxygen. When oxygen levels are low, such as what happens in the tissues, then hemoglobin will unbind and unload from the oxygen will unbind and unload from hemoglobin to the tissues. So we're going to measure how much oxygen is bound to hemoglobin, giving these numbers of knowing that hemoglobin has 4 subunits. So if all 4 subunits of hemoglobin are full, then we have 100% saturation. If 3 out of 4, it's 75%. 2 out of 4, 50%. 1 out of 4, 25%. 0 out of 4, 0% saturation. And now we're going to graph it. Don't hate me for this, you guys. I know I bug you guys about graphing all the time, but I promise this is a skill that you're going to need. So let's walk through this graph really slowly so you can understand the hemoglobin saturation. Okay, so what we have here is the percent saturation of hemoglobin. I'm just going to abbreviate hemoglobin with HB. So just to give you guys a visual, we're going to go from 0 to 100 on the hemoglobin saturation scale. So what 0 means is that all 4 subunits of hemoglobin are empty. 100% saturation means that there is oxygen in all 4 subunits. So hemoglobin is full at 100% saturation. So what would 50% saturation be? Here's our 4 subunits. How many do we have? 2 out of 4. So 4 out of 4 is going to be 100%. 0 out of 4 will be 0%. And then 2 out of 4 will be 50% saturation. And then 75% also turns out to be an important number. So how many in 75%? 1, 2, 3. Okay. So 3 out of 4 is 75% saturation. Now we're going to compare the saturation of hemoglobin to the partial pressure or the concentration of oxygen. And we're going to ask, how does this hemoglobin molecule behave in different environments? So our range of partial pressures are going to go back to the partial pressures I gave you before. So what were the partial pressure numbers I gave you when we talked about partial pressures of oxygen? Do you remember them? What's the partial pressure of oxygen in the lungs? Take a look at your notes. Partial pressure of oxygen in the lungs is 100 millimeters of mercury. What is the partial pressure of oxygen at the tissues? Remember that the tissues are using oxygen, so their partial pressure is going to be around 40. So we're going to have oxygen-rich and oxygen-poor environments. And we're going to ask, how cool is hemoglobin? And the answer is, hemoglobin is super cool. Hemoglobin has, at high levels of oxygen or in oxygen-rich environments, hemoglobin is going to be 100% saturated. And then hemoglobin does a good job of saving his money. So hemoglobin stores oxygen in the blood, and it binds that oxygen very tightly. But once it reaches an oxygen-poor environment, hemoglobin knows that there is need there, and this is an internal property of how the hemoglobin molecule works. And as it gets into these lower environments, hemoglobin starts to let go and unbind or donates. We're saying donates, right? Oxygen. So hemoglobin is going to unbind oxygen, and it's going to do so very, very well in these tissues. So in oxygen-rich environments, hemoglobin stores meaning that it is tightly bound to the oxygen. It will do that through most levels in the body. So in most cases, hemoglobin is holding on to the oxygen as it moves through the tissues. Right around a PO2 of, say, 60, which is still a bit higher, but it's starting to become oxygen poor, the hemoglobin is now going to start to let go of its oxygen currency. It's going to unbind oxygen and deliver or donate oxygen to the tissues. So now let's look at this graph. This is exactly what we just drew, so you guys shouldn't be scared of it now, right? The percent hemoglobin saturation is on the y-axis. 0 means no oxygen bound. 100% means all 4 oxygens are bound. So what is the hemoglobin saturation in the lungs? The hemoglobin saturation in the lungs, we need to go to the PO2 in the lungs, which is 100. And then we follow that value up to the line. Hemoglobin saturation in the lungs is at or very close to 100% saturation. So hemoglobin is going to store and hold on to oxygen when it reaches the lungs. Lots and lots of oxygen being held on, and it does a good job of saving his money until he gets to an oxygen poor environment. Now once we get into these oxygen poor environments, which are highlighted in blue here, what does hemoglobin do when it reaches the tissues? The PO2 in the tissues is 40 millimeters of mercury. So at a PO2 of 40, how much oxygen is on the hemoglobin? So let's look up here. Right there, we read that value, 75% saturated at the tissues. So, question, how much oxygen does the hemoglobin drop off when it reaches a PO2 of 40? How many oxygen molecules per hemoglobin? We went from 100%, which was 4 out of 4, to 75%, which is 3 out of 4. So on average, when the hemoglobin reaches the tissues, it's going to drop off 1 oxygen per hemoglobin molecule. It's going to go from 4 out of 4 to 3 out of 4. And if the oxygen level continues to drop or it reaches tissues that are extremely oxygen poor, hemoglobin will rapidly drop off more and more and more oxygen to try to deliver oxygen to the needy tissues. So hemoglobin saturation, or how much hemoglobin is bound to oxygen, is very much dependent on the cues in the environment. Oxygen is one cue, but it turns out there are other cues besides oxygen. So temperature, carbon dioxide, acid, and a metabolite called 2,3-BPG can also change the loading and unloading of oxygen. So it turns out that we can also change this oxygen curve by changing these values. So what I want you guys to think about is what happens in a tissue that is really, really active. A tissue that is really, really active is going to have increased temperature, increased carbon dioxide, increased acid, and increased metabolites. All of these things are going to go up in active tissues. So now the hemoglobin is not only going to drop off oxygen with respect to the oxygen levels, it actually will shift its behavior and become even more generous in highly metabolically active tissues. So in other words, at the same value of PO2, when we add these factors, high temperature, carbon dioxide, acid, and metabolites, then we will have even less saturation, meaning that hemoglobin will give even more donated, right? So we can see that they're not just needy with respect to the oxygen levels. We can add these other factors and they become even more needy. Hemoglobin will donate more. that actually is drawn here with this blue curve. So here's the normal curve I showed you, where you have 75% saturation of hemoglobin at a PO2 of 40. Now let's add these factors: high carbon dioxide, high acid, high temperature, high metabolites. This is what happens in active tissues. That actually completely shifts the hemoglobin curve over to the right. This rightward shift means that now at the same level of PO2 at 40, now instead of being 75% saturated, hemoglobin feels even more generous, and he goes down to 60% saturated. So an average of 1.5 oxygen molecules per hemoglobin will be donated in that same environment if we not only have low oxygen, but we also have high metabolites. This shift is described by the Haldane and the Bohr effects on hemoglobin. So the Haldane effect says that hemoglobin can sense and bind to carbon dioxide and acid. When it does that, that changes the behavior of the hemoglobin and will create the Bohr effect. The Bohr effect is when it actually changes its structure and makes it more likely to unload oxygen. So when hemoglobin binds acid or carbon dioxide due to the Haldane effect, it becomes more generous and unloads more oxygen. This is called the Bohr effect. Okay, so you get it? Oxygen, if we only measure oxygen levels, we get this curve. So if the hemoglobin is only sensing a change in oxygen, we stay on this curve. If hemoglobin, in addition to being in a poor oxygen environment, also sees a lot of other factors, acid, carbon dioxide, etc., it will become even more likely to unbind and donate oxygen to those oxygen poor, metabolite high areas. So 75% saturation normally, 60% saturation in high metabolite areas as well. That's the Haldane and the Bohr effects combined. Okay, that was oxygen. We're going to do carbon dioxide, and then you guys will be done for the day. Okay, so carbon dioxide transport is totally different. So carbon dioxide actually dissolves well in the plasma. So when we look at the percentages of how carbon dioxide is carried in the blood, we have about 10% that dissolves in the plasma as straight carbon dioxide, and 60% that not only dissolves but actually reacts with the water. So when carbon dioxide meets water and dissolves in the water, it actually forms carbonic anhydrase and bicarbonate. So it does this chemical reaction. So as carbon dioxide dissolves in water, it forms bicarbonate and gives off an acid. Hemoglobin can bind to carbon dioxide, and that's what we just saw in the Haldane effect. So when carbon dioxide binds to hemoglobin, that happens to about 30% of the carbon dioxide in the blood. So about 30% of carbon dioxide will be bound to hemoglobin, contributing to the Haldane effect, and 70% will dissolve. Out of that 70%, most of it reacts with water and becomes bicarbonate and acid. So as just a review, we're not done. We're not done yet, don't get excited. But let's just compare oxygen and carbon dioxide. Oxygen is mostly bound to hemoglobin, 98%. Carbon dioxide is mostly dissolved in the plasma and mostly dissolved as bicarbonate. So here's how it happens. Carbon dioxide is primarily then carried as bicarbonate ion. 60% of the CO2 in the body is carried in the plasma as bicarbonate. It converts to bicarbonate due to this reversible reaction with water, and I want you guys to memorize this reaction. carbon dioxide with water combines to liberate acid and bicarbonate. So the CO2 will enter the blood through the diffusion gradients that we talked about for the partial pressures of carbon dioxide, and then it will take several changes to react and become bicarbonate. It's actually naturally a slow reaction for the carbon dioxide to become bicarbonate in the plasma. But there's an enzyme called carbonic anhydrase that is a fast reaction to bicarbonate. So this enzyme is carried in the red blood cells, and that converts carbon dioxide to bicarbonate. The bicarbonate then will be put back into the blood plasma after the enzyme is able to work on it, and will be carried in the plasma as bicarbonate. So this is a tiny detail that emphasizes that you need red blood cells for this bicarbonate ion to be formed. Once it is formed in the red blood cells, there's a chloride channel that brings the bicarbonate into the blood. Yeah, I know, we need to draw this out. Yep, yeah. I told you today was going to be hard, guys. I wasn't lying. Okay, so you have CO2, which is produced in the tissues, right? That is going to diffuse into the blood and dissolve as CO2 in the plasma. About 10% will remain as CO2. The other 60% is going to enter a red blood cell. And inside the red blood cell is the enzyme, which I'm going to abbreviate CA, carbonic anhydrase. That enzyme is required then to convert the CO2 into acid and bicarbonate ion. The bicarbonate ion will then go through a channel and go back into the blood. So that conversion is 60% of the total CO2 produced in the tissues, which ends up being carried as bicarbonate. So 60% as bicarbonate because of this reaction that happens in the red blood cells, and then the transport of bicarbonate back into the blood. 10% will be straight carbon dioxide dissolved in the plasma, and then 30% will be bound to hemoglobin. From there, the carbon dioxide will be carried as bicarbonate, and it will travel to the lungs where the reaction will reverse to release carbon dioxide, and carbon dioxide will be transported out of the blood into the lungs. So here's a picture of that in your textbook. So the tissues are producing carbon dioxide. Carbon dioxide will dissolve in the plasma, but a portion of that dissolved carbon dioxide will enter the red blood cells. Once it enters the red blood cells, it will go through the reaction to form bicarbonate. The bicarbonate that is formed is because of carbonic anhydrase. Carbonic anhydrase makes this reaction go faster so that a lot of bicarbonate is formed, and then it will use chloride to put bicarbonate back into the blood. It will be dissolved then as bicarbonate, and once the blood reaches the lungs, this reaction will reverse. The bicarbonate will combine back with the acid to liberate carbon dioxide and water. That carbon dioxide will be dissolved and will enter the lungs and be removed by the lungs. So you can kind of think of bicarbonate as the carrier of carbon dioxide. So the carrier for oxygen is hemoglobin. The carrier for carbon dioxide is bicarbonate ion, and bicarbonate ion will be produced when carbon dioxide is high. Bicarbonate ion will release carbon dioxide when carbon dioxide is low, so that carbon dioxide can be removed. So, did you notice the acid? Right? So I told you in the very beginning that carbon dioxide has an important relationship to affecting blood pH. So increasing carbon dioxide in the blood directly increases acid in the blood, and when you have high acid, you have a low pH. So this is the acid portion of this equation. In order to prevent the pH of the blood from getting too low or creating a condition called acidosis, carbon dioxide must be removed by the lungs. Or if you have a condition where the blood is too alkaline, carbon dioxide can be retained to bring the pH level back down. So the amount of ventilation that we do, the amount of air that we're letting in and out of the lungs will increase if we need to get rid of carbon dioxide, and it will decrease if we need to hold on to carbon dioxide. So the brain is going to do this. The brain has regions that are going to regulate respiration, primarily to make sure that carbon dioxide does not build up. It's not that oxygen is not important. It's just that hemoglobin does such a good job of carrying oxygen that we generally, at most levels, have enough oxygen stored in the blood. And then it's plus or minus 1 oxygen as we go between the lungs and the tissues. It's really the carbon dioxide levels that are dangerous. So we have the medulla, the respiratory center specifically, which is going to coordinate breathing rhythm. It will coordinate the inspiration and expiration muscles. And there are 2 groups for that. There's the dorsal respiratory group, which controls inspiration, and the ventral respiratory group, which sets the basic rhythm. So this will control both inspiration and expiration during forced or active breathing. There's also a center in the pons called the pneumotaxic center, which will inhibit inspiration to allow the lungs to expire and recoil. There's another center in the pons called the apneustic center, which excites inspiration to enhance breathing. Problems with the apneustic center in the pons can lead to gasp type breathing, or apnea, sleep apnea. So this is the location of those regions. So the pons, remember, is sort of our belly region. If we look at the brainstem and the hypothalamus regions as our seahorse, the pons is up here. So these are the pneumotaxic and apneustic centers in the pons. And then here we have the dorsal and ventral respiratory centers in the medulla. Just one note, there's a lot of research that is changing on what is happening with the rhythm of breathing. So you will probably find in the next couple of years that this information will be updated. So how do we actually tell if carbon dioxide levels are too high? What we want to do for carbon dioxide is to have chemoreceptors sensing acid accumulation. So we have both central and peripheral chemoreceptors. First, the central chemoreceptors can stimulate or inhibit the medulla. They are mainly influenced by high carbon dioxide in the blood. So they're going to look at the levels in the blood. So we call the levels in the blood the arterial partial pressure. So the arterial partial pressure of oxygen in the brain has no effect. The arterial partial pressure of carbon dioxide is the main regulator in the brain. That's indirect because acid can't actually accumulate in the brain because of the blood-brain barrier, acid can't cross over to the brain because of the blood-brain barrier. So what happens is carbon dioxide crosses over first, and then acid accumulates as the carbon dioxide reacts with the water. So very, very sensitive levels of carbon dioxide in the blood that will affect the chemoreceptors in the brain. And they will increase or decrease activity in the medulla based on the need to remove this carbon dioxide. Arterial pH then is not directly sensed by the brain because of the blood-brain barrier. So it is the arterial carbon dioxide that affects the central chemoreceptors. But the idea is to prevent acid accumulation in the brain. The peripheral chemoreceptors are located in the aortic arch and the carotid body, so in the aorta and in the carotid arteries, and they are mainly regulated by levels of acid in the blood. So they're very, very sensitive to pH of the blood, and they will increase or decrease medulla activity based on the need to remove carbon dioxide. So they will directly send signals to the medulla to increase ventilation to remove more carbon dioxide. The arterial PCO2 doesn't stimulate the medulla as much as the arterial pH, but it can if it's very, very, very high, 70 to 80 millimeters of mercury. Do you remember the normal levels of PCO2 in the arteries? Normally around 40, right? So 70 to 80 would be twice that. Arterial levels of oxygen also don't affect these chemoreceptors very much, only if they're very, very, very low. So what is the partial pressure of oxygen normally in the arteries? Arteries should be carrying oxygenated blood. They should be at 100. Only if they drop all the way down to 60, this would be a major emergency, then will they send signals to the medulla. So the primary stimulus for the peripheral chemoreceptors is pH. The primary stimulus for the central chemoreceptors directly in the brain is carbon dioxide. In either case, when carbon dioxide is too low or when pH is too low, then the medulla will be stimulated to increase ventilation, breathe out and get rid of more CO2. So did you ever think when you were breathing heavy during exercise, did you ever think that that was because of carbon dioxide? No. So everyone thinks that they breathe heavy during exercise because we need more oxygen, right? So if you hyperventilate and you actually don't blow out enough carbon dioxide during that hyperventilation, you can actually spike your carbon dioxide levels even higher. So ventilation turns out to not be so much about oxygen levels. It turns out to be more important for carbon dioxide regulation. And that's what this is telling us. Phew, okay, I know that was a dense lecture. Take a break and I will see you guys next time. Let me know if you have any questions.